Section 6.4 is having us work with special products of multiplying polynomials together. So we have three main ideas that show up with this section and three main, I guess, patterns that we want to be looking for. The first two that we have listed at the top are this binomial square patterns that we have here. Now, if you would like to use these, I think the best way to think on all of this material is optional shortcuts. You do not need to use any of these shortcuts on any of the homework problems. You do not need to use them on any of the test problems. These are purely optional things that are available to us, and you can use them, you can ignore them. It's your call. Completely your choice. So our first two that we have are referred to as the binomial squares patterns. And this states that if I have two things that are adding together, then I can square that sum and I will always get a result in a pattern showing up here, also referred to as the square of a sum. If I have two things that are subtracting inside a set of parentheses and I square those, this is always the pattern of final answer that I'm going to get here, which we refer to as the square of a difference. Now, two ways you can do these problems. You can use this quote unquote shortcut that we have, which I think is just a lot of memorization for two very, very niche scenarios that show up. You can do that if you would like to. Or you can expand these things out, use the distributive property like we did in the 6.3 material, and get to your answer that way. A lot of people tend to prefer that, showing the work and doing the distributive property compared to these two shortcuts, and that's perfectly fine, perfectly acceptable, nothing wrong with that. It might take a little bit longer, but your call, there's nothing wrong with that. The main one that I do recommend that we have memorized is this one right down here. This very particular, very special product is one that you want to have memorized and have nailed down. This shows up quite a bit in our next class when we are working with factoring and allows us to reverse doing the distributive property. And we can use this as a really handy shortcut to save a ton of time there. So we refer to this as the conjugate pair of binomials. And a conjugate pair of binomials is where the first and last terms are the same, but the sum and the other is a difference. So one of them has an addition sign in the middle, the other has a subtraction sign in the middle. Otherwise, A is the same and B is the same. So that's the only difference that shows up between conjugate pairs. Now, the really good, really handy, awesome shortcut is this guy right here. If I have each of these conjugates or a conjugate pair multiplying together, like I have here, I will always and forever get to the answer of a squared, which is the very first thing squared, minus the second thing squared, b squared here. And I have nothing showing up in the middle here like I would with these other two problems. Now, again, if you wanted to see how and why this plays out, you would just use the distributive property. You would do A times A, and then A times negative B, B times A, and B times negative B. And you would combine like terms and see that things would cancel out. And there we go. We have our final answer. But this shortcut is probably of the three that we covered today. This is the one you want to have memorized. This is the one you want to be using. This thing saves a lot of time now, and it will save us a ton of time in our next class when we use this with factoring. And again, it should be stated with all of these products and everything that we're using, these are shortcuts that allow you to jump to an answer. Not as much work is needed, not as much work must be shown for them, and that's perfectly acceptable in these scenarios. Okay, so now I am Starting with my first example, and I have the square of a sum. I have two things that are adding together inside a set of parentheses, and they are all being raised to the second power. So I can use the square of a sum property that I have. I think it's very helpful if you are going to use that property, identify for yourself what is A and what is B. In this case, A is going to be 2x squared and B is going to be 6y. Now, if we reference our notes and see what it says our answer form should be in, this should be written out as a squared plus 2ab plus b squared. And I can just replace the a's with this 2x, and I can replace the b's with the 6y's and simplify my answer down. And here I have my final answer. Can't combine any like terms. Some of them have x's, some of them have y's, and all of the variables have different exponents in those respective terms. Now again, it should be noted that while this is an option that you can use, you are fully allowed to write this thing out in expanded form, meaning you can write it out as 2x squared plus 6y times 2x squared plus 6y, and then do the distributive property this way to get to your answer. Keep losing the little thing there. There we go. Well, I can write it out this way if I wanted to, and then use the distributive property to get to my answer. Nothing wrong with that. This is just an alternate option that's available to us if you would like to use it. So for example, 2, as we're going through this thing, yeah, you can expand this thing out if you wanted to do the distributive property, combine like terms, or you can use this shortcut that we have. And again, it's your choice on which one you would like to use. Both will work. One might be faster than the other, but kind of difficult to say. So if we were going to reference our general formula, that would say that we would have the first thing would be our quote unquote A term. So that'd be 3ab squared. And our second term, or our B term, would be this 5. I can then plug this in for A and B in the general one that we have here. And then I can plug values in and get to my final answer. And here I'd have my final answer. I always check if I can combine like terms, but I can't do that for this one because I don't have anything that has the exact same variables and the variables have the exact same exponents. So it's always good to check for that, as was noted in the chat. This turns out that we can't for this particular problem, and that's fine. So looking at number 3, we're coming to the parts that we really want to have these processes nailed down, or this shortcut nailed down, because this is going to save us tons of time. What are we noticing about the first 2 terms of these sets of binomials? They are the exact same thing. They are both exactly 9x to the third power. 9x to the third here, 9x to the third here. Awesome. That's my first requirement. If I look at the second term in each binomial, I'm noticing I get 4y squared. And I also have a 4y squared over here. Awesome. Now I look at the signs in between them. One's a positive, one's a negative. Doesn't matter which one comes first, which one comes second. This is a conjugate pair of binomials that are multiplying together. What's great about this, like we did with the previous problems, is we can define our quote unquote A term and our B term. I'll put the little quotes up here. For our A term to be 9x to the third, our B term to be 4y squared. And then I can just write this thing out in my final answer form with things substituted in. So instead of it being a squared, it's going to be 9x cubed squared. Instead of b squared, it's going to be 4y squared. And then I can get to my final answer from there. I can't do anything else from here. I have my final answer, and I am done. No properties or things to combine together, no like terms that I can combine together. That's just, here we go, all we can do. I think this hopefully highlights the power of this particular shortcut method that we can use compared to doing the full-blown distributive property and all of that good fun stuff. And for our last example, we once again have two conjugate pairs that are multiplying together. The first term in its entirety is the exact same as the first term in the second polynomial. The second term is also the exact same as the second term. Both of them are 2mn. And if I look at the signs in the very middle, great. One is a positive, one is a negative. I can go ahead and use my shortcut and get to this answer really, really fast. We can go ahead and label for ourselves again. Here's my A, and here's my B showing up here. My A term is going to be this 11m to the third n squared. My B is going to be this 2mn. And I know this is going to be in the form a squared minus b squared for my final answer, guaranteed. So I can just plug these things in and simplify down from there. And here we would have our final answer for number 4. And try and get all of these on the screen here as best I can. And yeah, this is everything for 6.4. So we have just some alternate ways that we can go about simplifying polynomials down if they're multiplying together. Again, you do not need to use any of these methods and these shortcuts if you do not want to, but they are completely available and fair game if you would like to do so. Section 6.5 has us working with dividing monomials together. So we had previous rules and we had previous exponent properties that showed up, and we have those listed here. These will still be showing up in these problems, but we're also going to bring in 3 new ones that are going to be visible now a lot more. And again, as mentioned at the start of some of these videos, the beginning of chapter 6, there is that general exponent properties overview page. I recommend to everyone take a look at that, write those down for yourself, have that quick cheat sheet of the exponent properties, because I think it's very, very useful to reference those as we go through these problems. So our new properties that we have are listed right down below here, and they are the quotient property, the zero exponent definition, and the quotient to a power property. So the quotient property, there's a few ways you can think on this. And at the end of the day, we want to think on which part of the fraction, the numerator or the denominator, has the bigger exponent attached to it. So what it states is if the numerator has a larger exponent attached to it, so in this case, a to the m is bigger than a to the n, then the result is going to go in the numerator spot, and I'm just going to subtract the two exponents together. If, however, the numerator's exponent is smaller or less than the denominator's exponent, I'm still going to subtract them, big number minus the small number, but the result is then going to be in the denominator of this fraction. The visual representation that I'll give for this is the following. I'm just going to do a hopefully a pretty straightforward one here. If I have a to the second power over a to the third power, I have more a's in the denominator spot. So if I were to expand this thing out, I would notice that two of the a's cancel here and here, which means I'm left over with a single, just the number 1 up top, and then a single a down below. So think of it in the stance of where is the leftover variable going to end up, in the numerator spot or the denominator spot? And that's going to be determined by if the numerator has a bigger exponent or the denominator has a bigger exponent. Just take a moment or so when you get to these problems, just take a look at that, observe on it, think on it for a second, and this is effectively what's going to be happening. We just now have a shortcut to do that versus having to write a whole bunch of A's or X's or Y's out on a piece of paper. We then get to the one that is both really straightforward and gives people a lot of headache, surprisingly, a lot of the time. It's the zero exponent definition. And what this says is any number that is not zero, that is raised to the 0 power, is always going to become 1. So I think the fun way of thinking on this is if I have, let's say, 5 to the 0 power, that's going to become 1. If I have, let's say, 293 to the 0 power, that's going to become 1. If I have negative 438 pi all to the 0 power, guess what all of this is going to be because it's a non-zero thing? This is all going to just equal 1, always and forever. So as long as the base, the thing that's being raised to a power, is not 0, then the result of that is always just going to become 1. Stuff cancels out and we get 1 left over every single time. And the last one that we have here is the quotient to a power rule. This is similar to the product to a power rule, which just states if I have a fraction showing up here, then I could rewrite this to be just the numerator raised to that power and just the denominator raised to that power as well, giving me a resulting fraction like this in the general form. We see this one show up a little bit more uniquely, and it's a little weird with how we can apply it. And we do have some flexibility with that, and I'll try and show that with the examples we're going to get to in a quick minute. Couple reminders before we get into our examples here is we will be utilizing all of these properties to simplify division with monomials. Every single one of these will be showing up in the problem, and we apply them in different ways. I recommend, as we are going through these problems, slow way, way, way the heck down and just use and apply one of these properties at a time as you are going through problems. A lot of people will see, hey, I've got the product rule, and I've got the quotient rule, and I've got the product to a power rule, and the quotient to a power rule showing up, and they're completely correct in identifying those properties. But where they go wrong is they try and use all of them at once, and man, it all falls apart really, really fast with that. So I would recommend referencing PEMDAS and let that govern what you're doing first, what you're doing second, third, fourth, etc. with these problems. Do not try and do too much at once. That tends to be where things go horribly wrong. So don't force it if you don't have to. Just do one thing at a time from one line to the next, then to the next, then to the next, and so on. At the end of the day, you're going to ultimately simplify it down to one single thing. If it takes you 5 lines, okay. If it takes you 2 lines, okay. If it takes you 50 lines, okay. Do what's going to help you track one step or one change to the next, and so on and so forth. Just don't rush yourself in these processes. That's the biggest thing I want to emphasize with this. Okay, I have x to the 43rd power divided by x to the 38th power. So this is where I'm going to need to use my quotient rule. The bases are the same and they are dividing, which means the exponents are going to subtract from one another. Now the question is the answer going to be in my numerator spot or in the denominator spot? And I can determine that by noticing that the exponent in the numerator is bigger, so my answer and whatever's left over is going to be in the numerator spot. And I'm just going to get x to the 5th as my final answer. Everything in the denominator would cancel out to become 1. And I have my final answer here. Nothing else needed beyond that. Looking at my second example, I'm given n to the 3rd divided by n to the 7th. Once again, the bases are the same and they are dividing, which means that these exponents are going to be subtracting from one another. Now, when I do subtract those exponents, is the answer going to be in the numerator or the denominator spot? And they're going to be in the denominator spot because the denominator has the bigger exponent. So I'm going to have leftover stuff down below there. I can write that out and get to my answer. And we're getting 1 over n to the 4th power as our final answer, and we are good to go here. You do also have the choice, if you would like to, of doing this exponent subtraction off to the side and then just writing it in place for the denominator for your final answer if you would like to also. Some people like doing that, and there's nothing wrong with it. Just make sure that you are following those steps properly and putting your final answer in the correct place afterwards. Looking at example 3 now, I have y to the 11th power divided by y to the 11th power. So we have 2 ways to go about thinking this, or 2 ways to go about thinking on this. Both will work. You can use either one of them. We can use the quotient property again, which states that if I have the bases as the same and dividing, then the exponents will subtract from one another. And if I do that, I end up getting y to the 0 power. Well, our property that we learned previously states that if I have anything that's raised to the 0 power, any non-zero raised to the 0 power, then this whole thing is just going to become 1 for my final answer, which might be slightly disappointing in the sense of we're used to seeing more variables in our answers now, but kind of nice in that, hey, this thing just becomes 1, nothing else showing up there. If you want to think of it and take the different approach, again, you could expand anything out, but really, what is any number that is divided by itself always going to be? Well, it's always going to be 1. 5 divided by 5, 10 divided by 10, negative 500 divided by negative 500. Anything divided by itself is always just going to be 1. So that's how we're getting this idea of y to the 0 power, or a non-zero to the 0 power always equaling 1 from. All right, so number 5, this is where we start to get some tricky stuff showing up. We start to have more potential operations, more properties that need to be applied in a particular problem. And that's fine. We just need to, again, take it slow and steady here. So I think it is worthwhile to start off looking at these problems saying, hey, I have that list of properties. Which ones look like they could be applied here? I think that's a good starting place. So I'm noticing that we have what looks like the power rule showing up in the numerator spot. And yeah, probably the quotient rule showing up eventually with m's in the numerator and denominator spot. So, okay, we've got some notes for ourselves of what's going on here. I think it's generally a good idea to try and simplify the numerator first, simplify the denominator second, and then see how they interact with one another. So let's start with simplifying the numerator down. We're using the power rule, and then we'll apply the quotient rule to get to our final answer afterwards, noting that we do have to follow PEMDAS as our guide for what we're doing first, second, and third. And I get m to the 13th power is my final answer. Power rule says 5 times 4 gives me 20. Then the quotient rule says I'm going to subtract these things together. I have more m's in the numerator spot, so I should have leftover stuff in the numerator of a fraction, and the denominator completely cancels to become 1. I'm looking at number 7. Again, more advanced, more weird things showing up here. If you are trying to do this problem all at once, that's where things are going to go horribly, horribly wrong. Do it in very small, very controlled parts. You can use PEMDAS and let that be your guide for what you're doing first, second, third, and so on. You need to. There's nothing wrong with that. And let's use that as we're going through this problem here. So PEMDAS would say I need to use parentheses first. Well, can't do anything inside the parentheses. That's just an a squared, and an a to the 4th. So parentheses are done in that regard. I can apply exponents, though. I have a squared raised to the 3rd power. I also have a squared raised to the 4th power. And then I also have a to the 4th raised to the 5th power. So I can work with each of these individual power rules that have been given to me, and then I'll see where I'm at from there. So I've applied the exponent property, the power rule, I should say, in the exponent step. Great. I can't do anything else from there. And now I can start to see in the multiplication division phase, which one do I want to do first? I would recommend let's continue consolidating and combining this numerator down together to be a single thing before we start looking at doing the quotient property. Otherwise, that could get a little confusing. So in doing so, I'm getting a to the 14th power, just applying my product rule. And now I see I have a single a to the 14th up top, and then a single a to the 20th down below. I don't have multiple a's up here and multiple a's down below. Now I can apply the quotient rule. And I have more things in the denominator spot. So 20 minus 14, that's going to give me 6. I should have the leftover be in the denominator of my fraction. So 1 over a to the 6th as my final answer. So I'm hoping we're seeing that there is some variability and some options on how we could go through these things. I'm hoping we're also seeing that there is a lot of room for potential error with this if you're trying to do too much at once. So again, slow down, do one thing at a time, then the next thing, then the next thing, and so on. And you will slowly but surely chip away at this problem and get it down to its fully simplified form. Trying to do too much at once is what gets people into trouble with these problems. So be careful if you're trying to do too much at once. We'll take a look at, yeah, we'll do number 8. That's the big terrifying one. So in terms of how we got to our answer here, we got a to the 6th from doing a squared raised to the 3rd power. So I applied the power rule here. That states that these two multiply. That gave me 6th, or a to the 6th. Power rule applied here, which gives me a to the 8th. And then power rule applied here, which gives me a to the 20th for my denominator. And then noting that I have multiplication going on in the numerator spot, and I want to condense my numerator down all together as much as I possibly can before I start canceling things with my denominator spot. So a to the 6th times a to the 8th, that's using the product rule, which means the exponents will add together. That gives me a to the 14th. So I have a to the 14th all divided by a to the 20th. Didn't change in that step. And then I have the quotient rule that I can apply here. I have 14 a's up top. I have 20 a's down below. 14 will cancel for both of them, or you could, off to the side, do this for yourself if you need to. And then we'll end up with 1 over a to the 6th left over at the very end. So tackling the beast that is number 8. Once again, do not try and do everything at once. Simplify this thing down in small, controlled parts. I think it's very good practice to say, I'm going to try and just simplify the numerator, and then I'm going to just simplify the denominator, and then look across this fraction bar and see what could cancel from both or not or anything like that. Otherwise, you run the risk of saying, well, I've got a y up top and a y down below, so part of those cancel. But then after I cancel that, what's the new part of that that cancels with this other y up here? It can get really confusing at that point in time. So just simplify the numerator using our properties that we have. Just simplify the denominator using the properties that we have. And then we'll get to our final answer and simplify it from there. So looking at the numerator, I have negative 12 x to the 6th y to the 9th times negative 4 x to the 5th y to the 8th. I can multiply the coefficients together. That's going to give me 48. I have x to the 6th times x to the 5th. I'm going to apply the product rule there, which means the exponents will add, and I get x to the 11th. And then I have y to the 9th times y to the 8th, which means the exponents will also add, and I get y to the 17th power. The denominator, I can't change that at all, so I'm just going to bring it down exactly as it is. Now the numerator has all of the coefficients condensed down to be just a single number of 48, which is awesome. All of the x's condensed down to be just x to the 11th, which is also awesome. And all the y's condensed down to just be y to the 17th. Fantastic. Now I can look at this thing and say, great, here's just the coefficients that are going to simplify, just the x's that are going to simplify, and then just the y's that are going to simplify. I'm going to do this over the course of several lines of work, but you could do this in 1 or 2 if you're able to keep track of everything. And here I have my final answer, negative 4xy to the 5th. So all I did is take a look at this and say, all right, I've been given, I have my numbers here. So 48 divided by negative 12, that's going to give me a negative 4. I didn't work with the x's, didn't work with the y's, so I'll leave those. That's what I got here. And then saying, I'm just going to work with the x's first. I have 11 x's up top. I have 10 x's down below. When I subtract 11 minus 10, I'm going to have 1 left over. The numerator has a higher exponent, so the leftover x goes in the numerator spot. I then have y to the 17th over y to the 12th. I would subtract those as well. 17 minus 12 gives me 5. The numerator has more y's in it, so y to the 5th is going to go in the numerator spot, and the entire denominator just became 1. We don't need to actually write the 1 in there. It is assumed and implied to be there, but yeah, this gives us our fully simplified final answer here. And that's pretty much everything for our 2 point, or not 2 points. This is our 6.5 material. I'm going to try and zoom this out a little bit so we can see hopefully a good chunk of the stuff. I'll go ahead and end the recording here, and I'll take any questions that you guys have over this or any other material that we've been covering.